Okay, cool. I'm just gonna mute. Okay, thanks. Um, okay, so some of you guys might recognize some of the slides from the last chat that I gave on the subject, but I just wanted to include them in here because I feel like quite a few people that didn't see the last presentation might be in this one, and so some parts I think are still worth just reiterating upon. Yeah, so this is just going to be like a little bit of a summary of what the landscape of Ethereum looks like at the moment, and like one or two related technologies. So I think like one of the first important things to do whenever talking about Ethereum is to just try to give a general sort of comparison between Ethereum and Bitcoin. And I know some of you have heard this a million times already, but basically Bitcoin, in terms of the protocol, is just, in a nutshell, you have accounts have balances, and those balances can be transferred between accounts. And so the blocks in the Bitcoin blockchain are effectively cryptographic representations of balance transitions that have been made between accounts. And like the thing that makes Bitcoin cool is that the cryptology being used basically guarantees that if a particular balance is being modified for a particular account, in the sense that its balance is going down and it's being transferred somewhere else, then you can be mathematically guaranteed that whoever made that transaction holds the private key for that account. And so every account it's a key pair, in the sense that you have a public key and a private key, and your public key is sort of like your public address, like what you would send money to, or somebody would send money to your public key, and then you use your private key to verify that you have permission to spend money for a particular public key. And so whenever you see a transaction being made for a particular public key, you can be guaranteed that the person who made that transaction had the private key. Like even if you had all the energy of the sun, you wouldn't be able to generate that private key like in a fraudulent manner. And so like you could go and steal the private key from somebody or do it through like more reasonable means, but you can't actually like brute force that private key, even if you had the energy of the sun. And then Ethereum basically takes that concept of how you have these strongly secured cryptographic transactions going on, and it applies that principle to basically a virtual machine. So like in a normal virtual machine where you have like at a low level assembly code, basically those assembly code lines effectively become represented as like cryptographic transactions. And so in the Ethereum virtual machine, each block represents state transitions. And so you could like any one of us could create a variable on Ethereum, and let's just say we called it like sovtech equals, and then we could say awesome or something like that. And then if that ever gets modified to a new variable, then there would need to be a corresponding state transition stored in a block in this blockchain, which shows that that variable has changed. And so with Bitcoin, the protocol itself is very much static or like locked down, in the sense that you can't go and create a new application on Bitcoin. But with Ethereum, because it's a virtual machine and because it understands this arbitrary programming language at a low level, it can understand arbitrary logic, and so you can build a new application on Ethereum. So another comparison that Vitalik Buterin makes quite frequently, Vitalik made Ethereum, is that Bitcoin is a lot like a pocket calculator, in the sense like a physical dedicated pocket calculator with the physical buttons on it and whatnot. So you go into the shop and you buy that calculator, and then when you leave the shop, that's what the calculator is. That's all it's ever going to be. You aren't going to be able to go and install like Angry Birds or something on your pocket calculator. But if you go and buy a smartphone, which is more like Ethereum, you can install an application that doesn't even exist yet on Ethereum. So the best applications that will be made on Ethereum arguably don't even exist yet. But because the protocol understands arbitrary logic, you can build applications that conform to that logic, and then you can deploy it to that virtual machine. And then it can run in a decentralized, distributed fashion in a censorship-resistant manner. Like, not even a government, if they wanted to, could go and change your application or stop it from working unless they found a vulnerability in the code. So this is, oftentimes you'll hear about ERC20 tokens, and I know I had this slide in the last one as well, but I just added a bit more here to give a bit more context. Basically, if somebody tells you that something is an ERC20 token, all that it means is that it implements this interface here, okay? And so all that it's saying is that this particular contract, here's an example of a contract, contains these functions in it. And they can take in these types of variables, and it describes like whether external contracts can call these functions as well. And if it's like the nature of that function within the contract, if it's just viewing data, or if it has the ability to modify data within the contract, and then it describes what it returns. And so these like interfaces are not actually describing everything about the contract. They're basically just saying that if you want to have an ERC20 token, you need to have all of these functions. They need to take these types of data as parameters, and they need to return these types of data as return items. And they have these events within them as well, and events are things that you can emit from within functions. So to like go a bit further with that, here for example you can see this transfer from, and we have the transfer from here as well, but all of this logic which is actually contained within the function is not part of the ERC20 spec. And so what's important to note there is that just because something is an ERC20 token doesn't mean that it's secure. It doesn't mean that all of this logic within it is going to be implemented properly, and people could literally do whatever they wanted to do inside here as long as it returns true or false, and as long as it takes these values in as a parameter. But everything else that goes on in here is like up to the developers. So yeah, just keep in mind, like if people say something is an ERC20 token, it doesn't mean that your funds are going to be safe in it, or that it is not going to be hackable or anything like that. And an ERC20 token is an example of a fungible token. And if you recall last week, Marlo gave a chat on non-fungible tokens. And basically like fungibility basically just means that every unit of this currency or of this whatever is interchangeable. So I've got an example here of an ERC721 contract, well, the interface, and in here you can, like, this is an example of an NFT interface, and this is actually like the main standard for non-fungible tokens. And so like the main difference here when it comes to non-fungible tokens is that every one of the tokens has its own ID attached to it. So in like kind of if you have rands, and physical currency is actually a bit of a not the greatest example of fungibility, because like a 1 rand coin from 1994, for example, might be sentimentally worth more than a 1 rand coin from 2020, because they have those years on them. And so they kind of, in a way, have like some identity attached to each coin. But if you think about a digital currency, like 1 Bitcoin is the same as 1 other Bitcoin. It doesn't matter. There's no ID attached to each of those Bitcoins, because ultimately in the contract itself, like inside this thing, there's basically just a balance which is getting changed for a particular address. So a non-fungible token is an example of a token that has an ID attached to it, and so you can't like just interchange them arbitrarily, because the identity of one token might make it a lot more special than some other token. Like, for example, if you have artworks or something like that being issued, then the artwork, like the Mona Lisa #1, might be worth a lot more than the Mona Lisa #1000 or something like that. And so that's like what fungibility means. And you can see here in the ERC 721 interface, they have these token IDs that are being used. And so you're checking like the ownership of like literally that single token, and they can't all just be exchanged arbitrarily. So another important component of Ethereum at the moment is something called DAI, and DAI is made by these MakerDAO people. They form the governance of this, and what makes DAI special is that it's a non-custodial stablecoin. And so you may have heard of stablecoins before, like there's Tether and like USDT or whatnot. I think those are even the same thing potentially. But like the thing about those is that you have this centralized organization that is basically, they have like a US bank account, for example, and then they have like custody of a particular smart contract on Ethereum. And whenever they mint like 1 unit of their smart contract currency on Ethereum, then they put like $1 into their US bank account. And so they are responsible for making sure that every unit on Ethereum is backed by 1 unit, like $1 in the fiat world. And that is like not ideal, because then you're basically trusting some random people to be making sure that every unit of a cryptocurrency is collateralized by a unit of US dollars or whatnot, and they can easily lie about that. So DAI is cool because instead what they've done there is there's basically a pool of ether, and that pool is like surrounded by a bunch of different smart contract mechanisms. And a smart contract is basically just the term for like an application that's been deployed to Ethereum. And so what happens there is that there's this pool of ether, and then every day these MakerDAO people, and anybody can buy, the token is called MKR, and it's basically a governance token of MakerDAO. And then people vote on what the price of ether is today in US dollars. Okay, and so if you have the price of ether in US dollars, then those mechanisms surrounding that ether pool can automatically make sure that there's just the right amount of ether in there, so that every unit of DAI is collateralized by $1, because you have the price of ether in US dollars. I hope that makes sense. Then there's quite a newish thing. Well, it's not actually that new, but it's gaining a lot more popularity, and it's called the graph. It is one word. And basically the concept here is that, like, if you want to read data from Ethereum smart contracts, like let's say you've had a contract running for a year, and every time somebody signs up, you want to be able to query those sign up events. If you were to actually try and read that from the smart contract directly, then you have to basically iterate through every single one of those events. Like, you would literally start at event like 0 as an index and just go through all of them until there are none left. And that is like something that can take an extreme amount of time. Like, it could take weeks if it's a really like popular application. And so what the graph does is it basically creates, you can run a graph node where it exposes a GraphQL API. And so when a dApp is just a decentralized application, when a transaction is made, then it hits the smart contract and the transaction takes place over here. This would be connected to Ethereum. And then that emits an event, and the graph nodes index all of those events, okay? So it comes through here and then it exits over here, goes into this WebAssembly module, which is responsible for basically indexing the events that you've described. So you basically create this document called a subgraph, and that describes all of the events that you want to index. And then it puts it into a store, which is like your database, and then this goes through here and exposes itself as a GraphQL API. And then your dApp can query that GraphQL API for those events which were emitted by the smart contract. And so you can like very quickly read historical data about a particular decentralized application without needing to iterate through all of them. And anybody can run a graph node, and they form consensus with each other. And so like it's a decentralized data aggregation platform basically, and it's really cool. Something else, this is fairly new, is called Aragon Court, and this is like a decentralized court system. So people can create disputes on Aragon Court. One caveat though is that both of the parties involved in a case are meant to be like in agreement that they're going to use Aragon Court for their case. You could like still make a case on here without having the other party subscribe to it, but so maybe for like sentiment analysis or something like that. But it's intended to be used with both parties agreeing to use Aragon Court. And then they have their own token called ANJ, which is Aragon Network Jura. And then basically you stake your ANJ tokens, and then you become a juror in this court system. And then if you get drafted into a case, you need to review the evidence that the case creators have put up in their dispute, and then you rule like whether you think that party A or party B is in the right or who's in the wrong. And it will select 2 other people as well. So each case has 3 people at the moment who are randomly selected from the pool of stakers. Although the higher your stake is, the higher the chances of you being selected. But that's still not like, it's not actually like you can just get the 3 highest stakes and then you'll be selected. It's just the probability of being selected goes up the higher your stake is. But there still is a random element to it. And then if 2 of the parties say that person A is in the right, but the third party says that person B is in the right, then person B will lose a bit of their stake, which they've put into this platform, and they can repeal that and then have new jurors selected, and then they can earn that stake back if the ruling was incorrect in the first place. And also the people who created the case can also repeal a vote. And so it's quite an interesting like thing going on here, where people are trying to create a decentralized court system so that we maybe don't need to rely on traditional courts anymore. It's definitely in early phases though, and like is not a replacement for an actual court yet, for a number of reasons. I think that one of the main reasons is Sybil attacks. Like that's still something that we need to work out, and I'll talk a bit about that later. But yeah, that's a pretty interesting thing. Then Aragon, the same group that made the thing from previous, Aragon is definitely one of my favorite like organizations on like building on Ethereum at the moment. They are making a lot of headway in terms of what they're doing, and they've created a JavaScript library called Aragon Connect, where you can basically like very easily fetch token holders for a particular token. This would be an Aragon organization that you've deployed onto their network, but you can very easily integrate your website with a decentralized autonomous organization which is deployed to Aragon. And so you would just put your decentralized autonomous organization name in here, and then you can view the token holders for that. And when you deploy an organization to Aragon, then it automatically creates your own Erc20 token. So that's the token that this would be fetching the holders of. and then you can manage like issuance of that token to different members, and like cap tables and voting and all of that type of stuff on your Aragon organization. And this just shows how you would fetch votes, like all the current polls that are going on and how to cast a vote in JavaScript. So it's like making it a lot easier for people to interface with decentralized systems within like a traditional web interface. Also, this is using Ethers JS, which if you feel like getting into like integrating your websites or whatnot with Ethereum, then there is an official Web3 JS library, but Ethers JS is maintained and was created by an individual, like as opposed to the Ethereum organization itself. And this is actually like significantly better. There are some cases where centralized, not really centralized so much, but sometimes if your application is too decentralized in terms of the development itself, like things start to become very difficult to change. And I think Bitcoin is a perfect example of that. It's almost like in a state of like, it's almost frozen in terms of the development because there was so much of an emphasis put on decentralizing the development processes themselves that now it's kind of like nobody can even come to consensus about what to do anymore. So like it seems like a better approach is kind of to centralize development at the beginning and then to slowly like decentralize it as time goes by, sort of the same as what's happening with Ethereum. And it's actually starting to become like essentially decentralized in terms of the development itself, but there still is like a core development team and that type of thing, and that allows for things to move quickly in terms of implementing new features and that type of thing. Yeah. Another platform that I'm quite excited about is called Monolith, and this is a decentralized finance platform, and it includes like a smart contract wallet similar to Argent, and it also has a Visa card involved in it. So basically the way that they do it, because they're trying to keep it non-custodial again, like they don't want to have power over your money. And so what you do is, instead of transacting in crypto directly, if you're using that Visa card thing, instead what you do is you convert some of your crypto into fiat, and then you can use that the money that's loaded onto that card essentially as fiat. But at the moment it's only available in Europe and the UK. So yeah, but I am looking forward to it becoming like more widespread. And they also do quite cool things like allowing you to, through their app, stake your crypto into platforms like Compound Finance so that you can basically generate interest on your cryptocurrency. And these people were actually initially called Token Card, but they rebranded to Monolith because they felt like the name was limiting to them to the card alone. But now they're implementing like a bunch of new features, like spend limits on your wallet and like things that go beyond just the card, being able to interface with other smart contracts via their application. So this is like just a quick comparison of different wallet providers that you get. Metamask is kind of like a nice Metamask and Argent, I would say, are both good for if you have not got that much money stored in it, right? So you should kind of think of these things as comparable to your normal wallet, or maybe a safe that's in your house or something like that. But don't put more money into these things than you would be comfortable having in like somewhere between your normal wallet that you carry around with you and a safe in your house or something like that. It's not a bank. Like this is not something that you should store your life savings in or something like that, because MetaMask is only going to be as secure as the password that you have set on in your browser to log into MetaMask. And Argent is only really going to be as secure as the password that you use to unlock your phone and to unlock Argent itself. So when you have like larger amounts of cryptocurrency, then what you're gonna want to use is a hardware wallet, and not all hardware wallets are equal. Trezor is another popular one, but like out of what is available right now, Ledger wallets are by far the best because they have something inside them called a secure element, which basically makes key extraction like extremely expensive. And so like one of the defenses that one of the problems with hardware wallets is that they aren't actually immune to physical attacks. They're really, really good against remote attacks, like completely immune to remote attacks. But when it comes to physical attacks, there's still a chip that you need to just extract a private key from, and then you can transact on behalf of that wallet. And so Trezors don't have secure elements in them. Ledgers do have secure elements in them. They also have a custom operating system that they've written for the chips themselves. And so like one of the benefits of something like a secure element is that usually you can use one of those oscilloscopes to like read the changes of the electromagnetic radiation like flowing through a chip, but to try and like deduce a private key whenever a signature is happening within that chip, whenever it's signing a transaction. But with a ledger, with their secure elements, they are actually immune to those oscilloscope attacks. So yeah, if you want something like really secure to store a significant amount of money on, then using a ledger is pretty much the best bet at the moment. Metamask is like really nice because you can use it to interface with web applications. So when you are in your browser and you're using a website that integrates with Ethereum, then like let's say you click send, like donate money or something like that, then it will pop up a little MetaMask thing, and then you can click accept and it will send the money. So this is necessary, but don't store like a whole bunch of money in it. That's basically what I'm trying to get at. Ethereum name service, this is basically like DNS of Ethereum. So like usually if you're using an Ethereum account, then the address that people would send money to, it looks like this whole big thing over here. So you don't really want to like give that to somebody. You can't really just tell somebody, hey, just send money to that. Like that's a bit much. And so instead what you can do with ENS is you can register an ENS domain essentially, and then you can map it to that currency. So then you could just type something like that, and then that maps to that address. So ENS is like a lot more useful for those kinds of purposes. But at the same time, like something that people need to consider is like connecting their own names to addresses. And this is only really like something that's becoming more apparent recently. Like there was a paper published about a month ago now where they went quite in depth into like de-anonymization procedures to try and expose who owns particular accounts and that type of thing. And so you need to be careful about like, don't connect something to your name if you don't want it to be connected to your name. Then another thing that is getting quite a lot of like praise lately, and it's generating a lot of excitement, is the concept of decentralized finance. And this would traditionally this would be a subset of like fintech, for example. But I wouldn't be surprised if, despite it being a subset of fintech, it actually kind of becomes like a term just as popular as fintech. And that because like over the last 7 days, for example, there've been about $350 million deposited into these decentralized finance contracts. $9 million are on Bitcoin in terms of this value here, and the rest, which is at like 1.63 or so billion dollars at the moment, is all on Ethereum, minus 9 million, which is on Bitcoin. And yeah, so this is something that's generating a lot of excitement at the moment, because you can do things like insurance, like put that on Ethereum, insurance systems, and like borrowing and lending protocols where you have interest that gets generated, and basically just normal like financial things. People are starting to try and decentralize those processes, and it's generating a lot of excitement basically. The next thing, I just want to quickly compare proof of work and proof of stake. So in proof of work, you're basically using like very powerful computers to process a very complex mathematical equation, and basically you're brute forcing a password. That's basically what you're doing. And so that takes a lot of computing power to brute force a password. And it's a password that is brute forceable, if I can put it that way, but it's like strong enough that it will take time and a lot of computational power for you to brute force that password. And so every time there's a new block generated on Bitcoin or Ethereum, then what happens is people have to brute force the password essentially to that block, and that's what the miners are doing. And with a problem with proof of work is, firstly, it requires a lot of energy to do that, like a lot of electricity, and so it's a bit wasteful, or actually very wasteful. Another problem is that because it's using computing power to do that, what happens is you end up having, like, if you have this network of nodes, like a mesh network of nodes, and they're all processing every transaction, and they're all having to brute force the same password essentially, unless they just accept the other person's attestation, which a lot of the time they do. Like if the block reward is already received, then not all of the computers are still going to process everything, but they should. And so what ends up happening is you have like a delta that forms between the fastest node and the slowest node, and so not every block has a predictable block time, and so there's a threshold or like a deviation from the norm which happens. So if the standard block time is usually like about 15 seconds, sometimes it'll be 20, sometimes it'll be 10, and so you can't like use the block number as a proxy for time, because the blocks don't always take the same amount of time. Another problem is that with proof of work, like all of these consensus mechanisms ultimately come down to like how much of the network is saying that things are a particular way, and then you have, that's considered the consensus, like whatever the majority of the people are saying things are that way. It's a lot like that even within like our societies and that type of thing. Like there could be this thing that is like really arbitrary and would probably be considered crazy to other cultures and that type of thing, but because you're within a community that considers something to be normalized, you don't really think too much about it. You just accept it because everyone else does it. And so what happens is, like, if somebody wants to attack the network, then they basically, like in a proof of work scheme, they just need to get more than 50% of the computing power, and then they can start forging the ledger and like telling everybody else that like Vitalik Buterin sent me all of his ether or whatever. And if you have more than 50% of the computing power in the network, then like nobody can say otherwise, unless they start to like specifically exclude those transactions. But then you end up with a hard fork. So you basically end up with a fork in the chains, and then the new chain needs to maintain a position of like disregarding what you said there. And then the problem is that if it's proof of work, you still have like more than 50% of the computing power, so you can just attack the new chain and you can just keep doing that. And so with proof of stake, like the cool thing about that is, instead of using computing power, instead what you do is you use your ether itself to mine. So what you do is, instead of using like GPUs, what you do is you say, here's 32 ether, and you put it in a contract, and you say, if I validate fraudulent transactions, then you can take my ether, or you can take some of it. It doesn't take it all at once. But if you like are out of the consensus, then and you have staked ether, then you'll slowly lose it. And so the benefit of that is, firstly, because you're not using like GPUs to do this, you get predictable block times. Like every block can be X amount of seconds, because you aren't waiting for the slowest one or anything like that. Another benefit is that you aren't using a lot of computing power, and so you aren't using a lot of energy, so it's way more energy efficient, like orders of magnitude more energy efficient, multiple orders of magnitude. And the other benefit is that if somebody starts attacking the network, then they lose their ether, and so they lose the ability to re-perform that attack with the same initial like assets that they had. So like with proof of work, you can't on an internet protocol take away somebody's GPUs, but with proof of stake on the internet protocol, you can take away their stake. And so you can basically make sure that like somebody can only perform the attack for a certain amount of time before they lose all their money, and then they need to reinvest that money, and they can't keep that going forever. So like the primary challenges, I would say, in the Ethereum space at the moment would be privacy, like just trying to disconnect individuals from their Ethereum transactions and whatnot. Another thing is the scalability of blockchains, and that has a lot to do with optimizing cryptographic proofs, because like cryptographic proofs like sort of archetypically require a lot of computational power, and so the less computational power that you require to make proofs, but still in a way that it like takes the right amount of time to make those proofs so that people can't try to create fraudulent transactions and that type of thing. There's a very like fine line between speed and security in terms of like blockchains in general, and trying to find that balance is very difficult, and also trying to make things efficient enough to be able to not take too much like hard drive space and that type of thing as the chain grows. It's very difficult to do that. So basically you want to be able to have like a small size on the hard drive, but still high security in terms of being able to verify every transaction was correct. Then another problem is like the usability of blockchain applications in general, or our metaphors. So like typically it helps to be able to compare a system to an existing thing that people are familiar with. And right now we're kind of challenged by how good the metaphors are that we use, like in terms of relating these new technologies to existing technologies and whatnot. But for the most part, like the internet up until now, and technology in general up until now, in terms of like globally adopted things, we have kind of been offsetting getting people to actually think about security. People make passwords, like that's what they're familiar with, and most people make really terrible passwords that are easy to brute force. And so like we need to at some point almost have a dialogue with ourselves as a society about like having stronger security practices, or we aren't really going to be able to utilize the true benefits of blockchain technology in like a really mass adopted sort of a way. Like what a lot of people now are doing is they're basically making it so that you need to use like your normal password kind of a setup, and then you just log into the website and it handles all of the blockchain related stuff for you. But when you do that, now the system's not that secure anymore. It's just as secure as your password, as opposed to being as secure as your the entropy of your key pair that you have on the Ethereum network. So yeah, that's something that we're going to have to confront at some point. I'm kind of thinking that it's going to be similar to how if you had to ask your grandmother like 10 years ago or 15 years ago or something to send you a WhatsApp message, they would be like, what are you talking about? And it probably would have been like this insurmountable sort of thing to imagine your grandparent like sending you a WhatsApp message like 15 years ago or something. But now it's like maybe a lot more of a reasonable thing to expect. And so people do just sort of naturally adopt new technologies and put the learning into using those new technologies if the benefit is good enough, which I think it will be with blockchain technology. So I think we're just going to have to bite the bullet, basically. And we'll see how that goes. Another problem is the Oracle problem. That, like if you remember at the beginning when I was talking about MakerDAO and them having that governance process where they vote on what the price of Ether is, that's an example of the Oracle problem. Like that governance community is basically the Oracle in that context, and they are feeding that real world data into the blockchain. So the blockchain can't just like it can't like go on to some exchange and look at what the price of Ether is today across all of these like off-chain networks. It can only sort of introspect upon itself. Like the blockchain can only read data that exists on the blockchain. It can't go and like figure something out, like start reading some random book or something like that. It needs to read data that's on the chain, and the only way that data gets onto the chain is by people putting it onto the chain ultimately. And so like trying to figure out how we can create trustless systems where we don't need to trust like centralized authorities or parties or that type of thing is a really difficult problem. Like who knows if this is even a possible thing to solve, but it is a big problem. Another problem is a Sybil attack. And that's basic. There was a woman named Sybil who had multiple personality disorder, and this like computer science problem is named after her. And basically, if you have a reputation system, then if you Sybil attack that reputation system or that voting system, then you just create a whole bunch of fake identities to sway the votes in your favor. And so that is easy enough to solve for if you have like a national government or something like that, where you have a centralized identity issuance scheme, like in South Africa, where we get our ID numbers or whatever from like Home Affairs or whatnot, and they've like got a monopoly over issuing those identities, and they have all these procedures in place to make it really difficult to get like multiple identity numbers to have multiple votes when you go and vote or something like that. But if you have a decentralized voting system where the issuance of those identities is decentralized, then it becomes a lot more difficult to control for those types of things, to make sure that one human being can only have one vote or one account or that type of thing. And so personally, this is my favorite like sort of challenge to think about and work on, because it's a very philosophically challenging type of thing, because one of the biggest questions when you're trying to solve for a Sybil attack is like, what is identity in the first place? Like, how do you actually identify a person, and what does it mean to like be acting as multiple people? And is there a way to like make it so that even if you did create multiple identities, you can still ultimately only like have as much attention as one person is able to give? And so can you make a system where Sybil attacking the network ultimately reduces the efficacy of your vote in the first place, so that you can be incentivized to rather just stick to a single identity? Then you have front-running attacks, which is basically like, let's say you have a decentralized exchange or something like that. Let's say you want to swap one Ether for X amount of some other token. Then when you confirm that transaction in Metamask, for instance, then what happens is you broadcast that transaction, and that transaction goes into a pending transaction queue, essentially, like a mempool. And then anybody can read that mempool. Anybody can read what the pending transactions are. And the order of those transactions being executed depends on how much each person is willing to pay for their transactions. And so if you see an incoming transaction for like $1 million in a particular token that is like a new token or something, then you can quickly like make a transaction for, let's say, $1,000 of that token and make your payment for that transaction higher, so that your transaction gets executed before that big transaction, and then you can profit off that that big transaction that happens after you now. So you can cut in line. That's the basic like premise of a front-running attack, is you jump ahead in the queue and you do something that you now know is going to benefit you after you've done that. Reentrancy attacks are basically when like you can kind of have this in an Ethereum contract, you can call like execution of arbitrary code, and that code can be passed into the function by a user. So you can encode a function call and you can put it into a contract if that contract allows for you to do that. And so a problem there when you do allow for that to happen is that you can call into another contract, and let's say it's something like a function that will change a monetary balance of somebody, okay? So what you can do is it changes their monetary balance, and then it gets to your function call and it calls into a different contract, but then you could program that other contract that it calls into, and you could program it to call back into the origin contract where the balance actually hasn't changed yet because the transaction hasn't actually it hasn't finalized yet. And so you can sometimes do these weird things where you can call back into an original contract where the value should be different now, but it isn't. And then you can sometimes like create like a loop essentially to drain funds out of that contract. And so yeah, that's something that you need to be careful about if you're allowing people to encode function calls and pass them into your contract. And it's very difficult to protect against. So like in general, I would just recommend not doing that, like not allowing your contract to have function calls encoded and passed into it. But still a lot of people do allow for that. Then you get flash loan attacks, which are basically a flash loan in the context of Ethereum is when you, like some decentralized finance protocols like DYDX, they allow you to borrow like the liquidity that they have locked into their contract, as long as you can borrow as much as you want, as long as you can pay it back within the same transaction. And so you can, like, these are scary because it means that a lot of the, like, let's say there's $1 billion locked into $1 billion worth of ether locked into their liquidity pool on DYDX, then you could literally borrow $1 billion and do some, like, call into a different contract and do something as long as you pay it back at the end, within the same transaction. And so that's a problem because a lot of the time, like, contracts kind of assume that they aren't going to get hit by a $1 billion transaction trying to do something. And so if you can craft a hack of a different contract within that transaction, then you just pay back the loan at the end and you walk away with that profit. And that's an example of like where reentrancy attacks also become a problem, because you're calling into other contracts. You're allowed to call into other contracts when you're doing a flash loan with DYDX, for instance. Then we have, this is an attempt at trying to have better anonymity on Ethereum. And the basic it's using ZK snarks, and ZK snarks, it stands for zero knowledge, succinct, non-interactive arguments of knowledge. They like the arg part and the n, it's like -i, so that this doesn't really make sense, like how they've made this, but that is what it means. Anyway, like the premise there is that you deposit, let's say, 1 ether into a pool of other 1 ether deposits, and then you basically camouflage yourself according to how many people are in there. So if the pool right now, the pool currently has about 3,000 people in it, and this is the URL, by the way. So if you put 1 ether into there, then you get a message back, and you can use that message to withdraw 1 ether from there. And so there's a disconnect created between the deposit and the withdrawal. So when you withdraw, all that an outsider who's analyzing the chain would know is that you were one of those 3,000 people, but not which one of the deposits you were. So that is pretty cool. This like brings us to the concept of like de-anonymization. So some like key things to keep in mind is that when you submit a transaction to Ethereum, then whatever gateway you're using, like if you aren't using your own Ethereum node, then you're probably using Infura or some other public Ethereum gateway. Metamask, for instance, by default uses Infura as their gateway. You can change it. You could put your own gateway in there, but most people don't. And so the point is that when you submit that transaction, you're trusting the gateway not to do anything malicious with your IP address. Another thing is that if somebody is trying to do like forensic analysis on the chain, then they can try to look at the times of day that a particular account makes transactions, and so they can try and put it into a time zone. Another thing is gas price distribution. So a lot of the time what you can do is you can look at a particular address, and you can look at a gas price is basically the fee that you're paying for the transaction. And so like a lot of the time, if you're using, let's say, Metamask to make your transactions, then it like Metamask is a lot of the, well, it does automatically fill in the transaction price for you. You can change it if you want to, but by default it's going to fill in the transaction price for you. And so what happens there is that you can a lot of the time determine that somebody is using Metamask, for instance, because their gas prices are always the same. And then you can try and correlate those with different addresses and try to form like a graph of connected accounts and that type of thing, but which might not have made any transactions with each other, but that do have the exact same gas prices being like set. Another thing is to actually just analyze the transaction graph directly. So to like look at all of the accounts that a particular account is transacting with, and to build like a mesh network of those and see what you can deduce from that, if you can get any of this information from each of those others, and maybe just one of them is enough to de-anonymize the entire set. Another thing which like this is something that I'm quite new to trying to understand is this Denon gift attack. And basically the idea there is that this is a diagram of it. So there's this protocol called Aztec protocol, which basically allows you to make deposits into like a little box here. We can just think of it like that. And an outsider can see that you made a deposit into that box, but they don't know how much money you put in there, okay? So they can't read when the value has gone down. They can't read when it leaves. They just know that this person put something into that box, right? And it's actually a really clever attack, because the thing about Ethereum is that when you're working in Solidity in your smart contracts, if you are, let's say you're working with a value of 1 ether. Now this ether is not actually ether the cryptocurrency, it's ether the denomination, which is a bit confusing. But basically, like let's say I make a new token called J, okay? And I have 1 unit of J in my contract. I'm working with 1 unit of J. Then 1 unit of J is actually equal to 10 to the exponent 18 way. Okay, so this is like the lowest denomination. And the reason for this is that in smart contracts, you can't use decimals. So there are no decimals, there are only integers. And so 1 is 10 to the exponent 18, because if you want like 0.1, for instance, then it would be 10 to the exponent 17. And so you always work with whole numbers essentially. And this allows you to divide 1 into a lot of different smaller fragments. And so with that Danon gift attack, what you do is you look, okay, somebody deposited ether into this, or deposited whatever asset into this box here. So what I'm going to do is I'm just going to put like, let's say, this much worth of Wei, and change these numbers to be some signature, like some random password of like digits, and deposit it into this box over here. Because the thing is, when somebody withdraws, then you can see that that fingerprint that you basically put into that box there is also being extracted out of there. And then you can attach this external transaction to the original person. And they have different addresses, but you can connect them because you basically poisoned that, you added a fingerprint to whatever's in that box. Because whatever's in that box, they aren't going to be modifying these values, because at this point it's like millionths of cents, and nobody like cares about how many millionths of cents they're spending. So you can like add an identifier to the end, to like the little pieces of ether inside there, and then you can connect the transactions to each other. So ways that you can sort of help with this is to like try to add like random intervals between transactions and that type of thing. Because a lot of the time when people use something like tornado.cash, then they'll make a deposit and then they'll make a withdrawal, and you can like see that somebody made a deposit and then made a withdrawal like almost within a minute or so of each other, and there's a very good chance that they were connected. Another thing is always to like use a fresh address when you withdraw from one of these confidential pools, and then also just in general to like try and change your behavior surrounding the whole thing, like to not try and you have the same behavior on one account as on another account. And this paper is like really good. It goes into like this stuff in depth. It's definitely the best paper I've seen so far on like de-anonymization of Ethereum transactions. This is just like, I just wanted to show this to give like a visual representation of what it means to scale layer 1 versus layer 2. So there's been a lot of success lately with layer 2 scaling, and basically what that means is like if this is your base blockchain, your base Ethereum blockchain, then you offset computation off of it, and you do all of this computation off the base blockchain, and then you make these periodic commitments to the base blockchain. If you were, so this is like scaling on layer 2. If you wanted to scale layer 1 in this instance, and like an example of this is called sharding, which is going to happen to Ethereum in the future, then you would basically have multiple ones of these base chains. Like you'd have another copy behind it, and they'd all be running in parallel basically, and have these things called cross links between them to make sure that they're all in consensus about what the current state is. ZK Sync is an example of a library that is ready for people to use right now, where you can basically create your own layer 2 scaling solution over there. You use ZK Sync, and that uses ZK Rollup, which is like the best current option for scaling in terms of layer 2. Originally there was something called optimistic rollups, but those didn't work so well because you're basically being optimistic about like the security of the system, and like there were quite a few trade-offs, like 2-week finalities instead of these 10-minute finalities. Although a big problem with things like even ZK rollup is that if you want to make these fast transactions happening off-chain over here and being rolled up, then you need to deposit your money into a smart contract, and then you can make your transactions, because basically like you put your money into, let's say, this block, and then it creates a tree similar to this one but of account balances instead, and then you can like change the balances within that layer 2 context, but you need to have your money in a smart contract, in a particular smart contract. You can't just make the transactions directly from your standard wallet. And that's a big usability issue because Metamask and those kind of things don't support those types of things yet. Loopring is an example of an exchange that's live on mainnet at the moment that is using that whole it's not actually using ZK Sync, but ZK Sync is an implementation of ZK Rollup, and ZK Rollup is being used on Loopring. So you can do thousands of very low price transactions on Loopring as an exchange. You just have to deposit your money into a smart contract first, and then you can withdraw it from there when you're done back into your normal wallet. But this has made a lot of waves recently because it's basically shown that like second layer scaling is done, like it's working. You can actually do thousands of transactions on there per second. And it still takes like a standard amount of time, like 15 seconds roundabout, to reach finality in terms of actually knowing for certain that that transaction was confirmed. But even at first when you make it, there's a very high chance that it is confirmed. Like as long as the system hasn't been hacked, like the web interface hasn't been hacked, you know that it's confirmed. And if the web interface has been hacked, then you probably have bigger problems than like that single transaction. So these are just the phases of Ethereum 2.0. We're very close to phase 0 being done. This will probably be done like hopefully by the end of the year on mainnet. Within the next 2 weeks or so, we're going to have a multi-client testnet, which will be an implementation of phase 0. So right now there's these Prilabs people are if you go into this blockchain explorer, you'll be able to view the Ethereum 2.0 testnet blocks, but it's only one client that's being used at the moment, which is the Prilabs client. But yeah, within the next 2 weeks, we'll have these other 3 clients, and all of those clients are going to be like connected to one another. So that's really exciting. I know that I'm over time though, so I'm just gonna like skip these things for now. A bonding curve is something that and also like I don't expect anybody to stay. I'm just gonna get to the end of it. A bonding curve is basically something that you'll probably see a lot as the space matures and that type of thing. But when you see these things, don't assume that this is a price chart, okay? Because we've kind of been conditioned into thinking that this axis at the bottom here, like the x-axis, is time, but this is not time. This is the token supply, okay? So it's basically the number of units in circulation of the token, and then the price is the y-axis. And so what happens in a bonding curve is, as the token is, when people buy the token, if you're interacting directly with the bonding curve contract, as you buy it, it mints units of the currency, and they will follow a predefined curve. And as you sell them, you can sell those units back to the bonding curve contract. And when you sell that collateral, then you get back the money that was originally put in, like some amount of it, whatever the price of it is at that point. But then it burns those tokens. And so like what would happen in reality is this thing would go up to some point where people think that it's like should be, and then it will sort of oscillate going up and down this thing. And so your price chart would actually look fairly standard, like in terms of going up and down, and it could be volatile or not. But ultimately this is not a time-based chart. Like it's just as people buy, the price follows this curve, and the supply is increased. And as people sell, the supply goes down, and so it goes wherever the intersection is between the supply and the price. And so a bonding curve, like in essence, is just the price is equal to a function where your only parameter is the supply. And that can be defined however you want to define it. Next thing that I just want to show quickly is Uni Swap. And this is my favorite exchange personally. It's a decentralized exchange, and I'm actually just going to show a quick transaction here. So I'm going to buy some of this Ant token because I really like it. And I'll just do this amount. And so we can see here when I click swap, then my Metamask pops up. So here's Metamask, and it's asking me to confirm this transaction. What I'm going to do is I'm going to edit the gas price here. And in general, what you should do is check like this website to see what the current gas prices are. So here we can see it's 42 if you want to get a fast transaction through. And for the sake of this, I'm just going to do that because I want it to be fast. My computer's just a little bit slow at the moment. So we're going to set this gas price to 42. It would have taken a while there. That's why you should always check this, because it could actually be like low enough for it to take a significant amount of time. And then we confirm that. And now it's broadcasting the transaction to the Uni Swap, to the Infura gateway. And then the miners are going to mine that transaction, and then hopefully it will be confirmed. And then we'll have that those Ant tokens within our Ethereum account. So yeah, that usually takes like a little bit of time. The network is also under quite a bit of strain at the moment. So it might take a sec. We can actually view it on Etherscan as well. This is usually a good idea too. Okay, we can see that it's going to take like around a minute. So I'm going to move on to something else in the meantime. Okay, it was just confirmed actually. It showed on my other window. So there, that was confirmed. And now we have those Ant tokens. So we just made a decentralized exchange like on the base layer. And that is completely final. Like nobody can turn that back now. If Donald Trump wanted to reverse that transaction, he could go and screw himself effectively. Like there's nothing he can do about it. And there's a lot of power in that. This is like a visual metaphor of a ZK snark. So there's this Alibaba's cave metaphor. And basically the concept there is that, let's say you have Alice and Bob here. What Bob goes over there, okay, and he waits on the outside of this cave. And Alice goes in here and picks to go either A or B, okay? Then Bob comes in and he shouts for Alice to pop out at either entrance A or B, okay? And if Alice pops out at A, then he has like some idea that either Alice went to A initially. Like that's a key thing to remember, is that Bob doesn't know whether Alice went A or B. And so when Bob says come out at A, like he can't be sure just from that one time that Alice didn't also pick to go and wait on A side. And so what happens is you repeat this process many, many times. Like let's say you do 1,000 rounds of this. If every single time that happens, Alice comes out of the place that you said, then you can be pretty much guaranteed that Alice has the key for whatever that secret is. So you need to iterate it like that to have any form of certainty. But the more rounds that you add, the higher the certainty becomes. NuCypher is cool because, like, traditionally if you encrypt something, then you need to encrypt it for each person that you want to be able to decrypt it. But with NuCypher, they have this thing called proxy re-encryption, and basically you can take an encrypted file and re-key it for a new public key. And so a new person can decrypt that file. And it actually uses like fully homomorphic encryption, where it can run computation on encrypted data. So I definitely recommend checking out this stuff. It's really cool what they're doing there. Decentralized autonomous organizations, those are just like what I was speaking about earlier in terms of having like MakerDAO voting on the price feed of Ether so that they can have a stable coin at the end of the day. These are a few other interesting ones in case anybody wants to look any of them up. IPFS, Nuz is going to be speaking more about this next week, but this is it plays really well with Ethereum, because the thing is like it's really expensive to store data on Ethereum. And so what instead you do is you upload a file to IPFS, and then you get a hash of the file back, and then you store the hash of that file on your Ethereum blockchain. And then whenever you want to get the file, you can request the file by its hash from the IPFS network. And so it's quite interesting because the address of the file, like you request the file by a checksum of the file. So you're pretty much like guaranteed to be getting the file that you want. And you can even hash the file when you get it back and perform the checksum yourself, which is nice. Quadratic funding is also a cool thing. It's basically just the concept of like, if you have a bunch of funds, then if you have a pool of extra money which subsidizes those funds, then what you do is you take the square root of the amount of money that has been donated to a particular fund to get the portion of the subsidy pool that it will get. So like this is cool because it makes it so that if you have some curated list of funds, then like if somebody wanted to Sybil attack that kind of a network, they can't really Sybil attack it, because as they put more and more money into one fund, their returns diminish like very quickly. And so the problem that still needs to be solved with quadratic funding is that the curation of the funds, like the options of the funds, can be Sybil attacked. Like if you allow people to just arbitrarily create new funds and then make small donations to each of those funds, then they can drain a lot of the pool. And so there needs to be like some sort of centralization at the moment in terms of curating which funds are available. But as long as that's done like properly, then the actual donations being made to those funds can be done in a Sybil resistant way, which is nice. And this is currently live, so like people can create applications for funding on this Gitcoin grant section, and then they price match everything, and then if you get like some DAI donated to your fund, then the subsidy pool adds more DAI to it. And yeah, like people are making are getting funding through that like quite readily. And yeah, that's it. Thanks.